Hello, hello. So here we're going to look at power and efficiency. We're going to start off with power. So in the previous unit, we looked at all kinds of power, all kinds of energy changes. Well, not all of these. Some of these we'll save for later chapters in AS and A2. But basically, this is a summary of all kinds of different energy changes that can happen in the world. There are definitely more, but these are some of the more common ones that we will look at. So the basic idea is you got all this energy to do work, all kinds of work. And work is basically a change in energy. Okay, so either you are the one losing energy to do work, or you are the one where someone else is doing work on you and you are increasing in energy. So the perspective is just the thing that's different, and that's related to the positive negative sign. Are you the one getting energy, or are you the one losing energy doing the work? Okay, so that's all the positive signs and things like that. In this video, we're going to look at an extra thing called power. You're going to learn how to use changes in energy to calculate the power of a system, or the power of, I don't know, a force, power of you doing something. So that's what we're going to look at, power. Let's start off with a kind of brainstorm question. I'm going to show you two pictures and we're going to think about which one has more energy, is more powerful. So on the left side, we have this character loading up a ball of energy in his hand. Okay. So this ball of energy is 9 times 10 to the power of 13 joules. And if this ball of energy hits you on impact, in 0.0001 second, all this energy is going to be transferred to you. So like, boom. Okay. So you don't want that thing to hit you. But if it does, that huge amount of energy is going to hit you. On the right side, we have another character. This is character A, by the way. This character is shooting a laser beam, or a beam of energy. It's almost the same, 12 times 10 to the 13 joules in 5 seconds. So if it hits you, it will hit you for 5 seconds and release that amount of energy on your body. Oof, you don't want to get hit by either one of them. So between those two characters, one is throwing a ball of energy at you, one is shooting a beam of energy at you. Which event released more energy on impact? Well, you can look at the amount of energy. Joules is the amount of energy. So I would say character A released more, character B. Why did I say A? B released more energy. Because this one is 12 times 10 to 13, which is more than 9. So there's more energy in that beam overall. But then, people complain, this is hypothetical. People say, well, why does it feel like A is more powerful upon impact? It's like got more power. But why? How do we make sense of that? It's something to do with the time where that energy is released. So they both have kind of the same energy, but what's different is the time where that amount of energy is released. So actually, A is actually more powerful on impact. That's correct. That's what people feel. And that's because the rate at which energy is released is much higher. Oh, this got cut off. Higher is the word. Okay, so maybe this guy on the right, he released that amount over 5 seconds. So it's like, okay, so that's the power of it. Whereas the guy on the left, it's like in barely 1 second, it's like, boom, and you get all that energy right onto you. So so in that sense, this fella has more power, but the one on the right has more energy in total. Okay, so more power, more energy, both equally deadly. So that's the general idea how to think of power, which is why bombs and explosions in the world are so deadly, because they have so much power released in such a short amount of time. It goes boom, deadly. Compared to something, let's say the earth turning, that's a lot of energy too, but it's not like a sudden kind of release of energy. I don't know. So go look around things in life where the power is different. So now a formal definition for power that you can write in A levels. Don't write like, oh, guy A released an explosion, guy B. No. In A levels, you want to say that power is the rate of work done on an object. So rate here is an important thing because time now comes into play. So let me make a note. Rates, when you see this word, it basically means time is a factor in here. How much time actually matters. So, what is an equation for this? You may remember this from previous courses in IG or somewhere else. But the idea is power is related to your change in energy. Or in other words, power is the work done over a certain amount of time. So that's the rate. How much energy is released per second, per second, per second. Okay, so this one is the, you say the general formula to remember. Power is the work done. I should put here WD, work done over the time. So you may guess, okay, the units of this is joule per second. How much joules is released per second? But there's also another unit that people have come up with. And this is related to a guy, a famous guy. It's named after him actually, and this is the unit of watt. W. So watt is the unit of power. There's a name for it, or you can express it as that. If you want to break down the J to base SI units, you can still do that. Go break it down. Force times displacement and everything. So watt is the unit you will commonly see, the W. Oh man, so many W going on here. So this is W, D, that's the symbol. And here W is the unit of power. So if you look at a light bulb, maybe a heater, a cooker, just look, it will say 200 watts, 500 watts, 600 watts, 2000 watts. These watts means how much energy is the oven using per second. Okay, now actually, work done by right officially, if you follow the maths way of writing things, you should actually write the rate of work done on the object should technically be written like this, dW dt. That's dW means change in work, change in time. But if I can use this form to generate a secondary formula for this, how to calculate power. And here's how we can do that. Now previously we know that work done is force times displacement, right? Okay, assuming these are vectors, but if they're in the same direction, they're parallel, you can pretty much ignore the vector part of it. So this is change in force times displacement over time. Okay, you don't have to write the D's, but well, if you do write it, then you're following the normal maths convention. So normally we'll say the force is constant, so what's left is ds over dt. Now ds is a change in displacement over change in time, which is also velocity. Okay, so here is velocity and force, also vectors. I'll just write out the vector part for you. So you should know how to use this formula, and where it came from is basically just plugging in this inside here to expand the formula a bit. So, but it's handy because it gives you another way to calculate power. It's the same thing, but it's a shortcut. Also, side note, this, if your force arrow and your velocity is in the same direction, then you can pretty much just ignore the vector. But if it's not in the same direction, for example, if this box is moving here, velocity, but it's pulled by a string upwards, so they're not aligned, there's an angle between them. This is a throwback to our very first video on work done. So if they're not aligned, then you have to resolve the component FV cos theta. This is a reminder, okay? If your forces and the direction it's moving is not aligned, it's like pointing somewhere else, okay? So this is one way to think of power. One last final way. It's related to this one. It's just a matter of definition. So work done is kind of a change in energy, right? So another way you will see people talk about power, this is the last one, is how much energy is released in a short amount of time. So you can say it's a change in energy over a short amount of time. What time is that? This is basically another way of saying the first equation. Okay, so you'll see common equations is P equals to W over T, P equals to E over T, P equals to F times V. But all these stem from the same idea that power is the rate of work done. Another one, okay, so here rate of energy transform, but stick with this one over here. Energy transform, work done, same idea. So this one is to give you a heads up. Electricity can be involved in work done. I didn't show you any electricity equations here, right? But here I'll give you a heads up. So let's say you have a phone battery that can store up to 39.6 kilojoules of energy. It's an estimate. You know, different phones got different capacity. So you're using an adapter to charge your phone. How does the adapter look like? Then the thing where you plug your phone into the socket and you charge. You use an adapter with an output current of this 2.4 amps and a potential difference of 5.2 volts. That's a standard for most chargers that has a USB port or if it's a direct charger. So here we have a problem. What is the minimum hours required to fully charge a dead phone? How on earth would you calculate something like this? Well, we just learned about power. Power can be the change in energy over time or, well, let's use the change in energy over time. So change in energy over some time. And we know the phone battery can store this amount of energy. So if the phone is dead, you're going from 0 joules all the way up to fully charged 39.6 kilojoules of energy. Oh, so we do know the change in energy. But do we know time? We're trying to find that. Do we know the power? What is the power of your charger? This is where it'll be handy to get a sneak peek of a future chapter. So in the future, in some of the electricity chapters, you will learn that the power in a circuit can be calculated by the current times time. So current we say is I times, current times potential difference or voltage. So I is current, voltage is potential difference, PD or voltage. So this one, hang on to this first. You might need to use this a little bit in this chapter to calculate power for anything electricity related, but we will learn the full details of this P equals to IV properly in a future chapter. So P equals to ET. Well, we can find a change in energy, so that's 39.6 fully charged times 10 to the power 3 kilojoules minus 0 if your battery is dead, and time. And on the left side, we can calculate that with I times V. So current is 2.4 times 5.2 volts. There we go. Let's see how long it takes in hours, by the way. So 2.4 times 5.2. Sorry. 39.6 times 10 to the 3 divide by 2.4 times 5.2. So that gives us about many seconds. If I convert it to hours, I will get roughly 0.88 hours. Wow! That's like 52 minutes. That's really, really fast. In real life, I don't think it takes this short amount of time to charge a phone. There's a reason for that. So ideally, in theoretical calculation, your phone should charge pretty quickly in less than an hour, from 0 to 100%. But in real life, there's actually a lot of energy loss. So maybe the battery heat up, the charger heat up, some energy loss, no friction. I mean, friction in the circuit is resistance. So your charger is not, your wire is too long, you lose some more energy. So you lose a lot of energy. So actually you would take, in real life, more than 1 hour to charge. Okay, so in the next unit, we will look at what we call efficiency. Okay, there are a lot of energy loss. So this amount that you put in, this power you put in may not be what your battery is receiving because the energy loss here. Energy loss there, get hot here and all kind of thing. So efficiency will be something we'll talk about in the next unit. But just so you know, real life doesn't matter, doesn't always relate with theoretical calculations like this. So remember, PIV for electrical systems. Now let's look at something that's not electrical related. Or is this electrical related? Let me see. Oh, it is electrical related. But we have a graph. Now, this graph on the right shows the energy changes in time. And this is for an electrical generator. So electrical generator during the first 5 seconds is shown. Okay, what is the maximum power generated at any instant? So at any point along this 5 seconds. How do we find power from an ET graph? Remember I talked about how power is a change, energy release over a unit of time. Okay, the more proper mathematical way, why do my words keep disappearing? Release. The more proper way to write this is change in energy over change in time. So, whenever you see this delta E, delta T, this means this is also the gradient of an ET graph. You know how like dy dx, change in y, change in x is the gradient m? Okay, so in this case, if we can find what is the maximum gradient of this graph, where is it the steepest, the most steep slope, that will be the maximum power. So on this part down here, not as steep. Here kind of, ooh, this one looks very steep. Okay, then this one is less steep. So here, what is the change in amount, change in energy over that time? So I'm going to look at this part now. So here, the change in energy is going from 10 to 40. So 40 minus 10, final minus initial. And the change in time, delta t, is 3 minus 2, so just 1 second. So this is basically finding the gradient out, which is also the change in time. So what you get is 30 divided by 1, so 30 watts. So here we can say that the maximum power generated is 30 watts, and that occurs somewhere between 2 to 3 seconds. Suddenly, it's a very quick change in energy, so lots of energy coming out. Okay, so reminder here, power is the gradient at this of this graph at this straight line here. Thankfully, we only look at straight lines, because if it's curvy, we have to do some math stuff there. So remember, gradient is power for this ET graph. Now, let's look at something fun, a toy aeroplane. Oh, airplane engine. So aircraft travel at a constant velocity in a horizontal flight. Now there's some forces acting on it in the diagram. The mass of the aircraft is 2000 kg. What is the power produced by the thrust force? Pause the video from this one if you want to take some time, and then come back and see how you can solve a question like this. By the way, this is on page 19 if you want to try it out on a piece of paper or the printout if you manage to print it out. So let me give a second to get there. This page. Okay. So what's happening here is your aircraft is traveling at constant velocity on a horizontal flight. So if I want to label all the forces here, constant velocity v of 90 meters per second means that there's no net force, it's just cruising, which means the drag force should be cancelled by a thrust force of 2,400 newtons. And the plane is not falling down, it's not going up, it's just steady on a horizontal flight, which means the weight mg is equal to some other lift force. I don't know what is it, but it should be also mg because it's not going up and down. Okay, so then how do you calculate the power produced by this thrust force? Well, you will say, oh, can we do power is work done over time? Yeah, but we don't really have the work done, so it's kind of extra work to do that. Or what if we look at change in energy over time? Oh, we also don't have the information. How about current times voltage? No, there's no current, no voltage here. So what's one more we forgot? Force times a constant velocity. Yeah, we could use that. Let's use this. In fact, a quick note, when you're using power equals to force times velocity, we're assuming that force and velocity is force is constant in this case, and your velocity is not instantly changing, okay? So at this instant, it's 90 meters per second, and your force is constant. So here, we can just use power is, we want to look at power by the thrust force. So how much power is this force exerting? So you have 2,400 newtons. This is newtons times velocity of 90 meters per second. So this thrust force is likely from the engine, the propeller, everything lah. So then you have, let's see, 2,400 times 90. Wow, that's a lot of zeros. I'm going to press my calculator, the ENG on my calculator, the ing button, to give me a nicer number. And I should get about 216 times 10 to the power of 3 watts. Oh no, the answer's in 10 to the power of 5 and 6. Okay, sure, let me do that. 2.16 times 10 to the power of 5 watts. That will be B in this case. Okay, so just remember, power, usually you can relate it to a force that is pushing an object or something like that. And this is one case of it for an airplane. So just now was something on the air. How about something on the ground? Here, you have a car straining uphill. Thankfully, they gave us a picture, so we don't have to draw it. So a car is traveling on a horizontal road. And engine has some power to keep it going. Then the car goes up the slope, but it still has the same constant speed. Wow! What is the output power of the car engine when traveling up the slope? Now, before you do any calculations, think about this. Do you think the car engine needs to give out more power when it's going up the slope? The answer is yes. Why? Because if you give out some power and you travel at 25, then suddenly you're going uphill and it's still 25, means your engine is like giving out more power to counter the slope. So you will hear, maybe you're on a flat road, you hear the car, then you go uphill, because that's the car engine kind of give out more power to maintain that same constant speed. So pause the video if you need to, try this out, see how we can solve it. This is on page 16 if you have that print out and you want to try it out on a piece of paper. Okay, how to find this thing? Well, first I'm going to do some force drawings to help us think about forces and how that relates to energy. So we said in the beginning, the car engine is giving out 30 kilowatts to get us moving at 25 meters per second. What force is that? How much force is this engine giving us? Well, we can check that easily. So power is force times the velocity. So we have 30 kilowatts equals to force times 25. So the force will be about 1,200 Newton. Oh. So actually this car engine is giving out 1,200 Newton. So 1,200 Newton relate to a power of 30 kilowatts. Hey, but wait. I thought constant speed means the net force must be 0. Why got 1,200 in front? Don't forget there's drag force. Frictional forces and drag forces. If you're traveling at a constant speed, means the net force is 0, means there should also be a drag force or resistive forces of 1,200 newtons. So that's the beginning part. Later, we see that, oh no, we are now going uphill. So what is the additional force that is kind of opposing the car's motion? So we have an additional force here. What is that? What is causing the car to slide down? Weight, gravity. Gravity wants to pull the car down. So previously, although we have a weight here, it's perpendicular to the horizontal, so it has no horizontal component. But here, weight is on a slope, so there is a horizontal component. Horizontal means this is what we call our horizontal. There is some component here, and this is what we call the WX component. So we need to find that. Okay, throw back to your dynamics and forces. So if we have an inclined plane of 2 degrees, you have mg. We're trying to find the vertical and horizontal component of weight. This is the horizontal one. And this is the angle 2 degrees. What is WX? WX will be, in this case, mg sine 2 degrees, which is about, I think I wrote it down, 480 newtons if I round it off. So 480 newtons. Oh my. So once you start going uphill, you have an additional 480 newtons that the engine has to fight against. Means this has to be 1,200 plus 480 newtons if you want to keep the same speed. So your poor engine now has to crank out this much power to keep going uphill at the same speed. So how can we calculate the power output of the engine? There are two ways to do it. Here's the first way. We already know at first the engine have 30 kilowatts that gives us 12,000 newton. So the additional power needed is, you can take force times distance. So the additional power needed to counter that weight component is 480 times, and you're at a speed of 25 meters per second. So this is 400 is the additional power you need to fight against the weight of the car. That will give us 12 kilowatts. So that's extra power we need, which means the total output of the engine needs to be the original 30 kilowatts plus the extra 12 to fight against the weight. So that will give us a total of 42 kilowatts. Okay, don't forget to add the 30, that's the original. Now if you're wondering, is there another way if you don't want to find additional? Well, yeah, you can calculate the total output straight away. If you want to use forces, you're more comfortable thinking of forces, sure, you can do that. So total power output, F times V, can be 1,200 plus 480 times the velocity. So to double check, 1,200 plus 480 times 25. So you should also get a 42 kilowatts. So there are two ways to do it. If you are more comfortable drawing force diagram and trying to decide what is the force, you can use this method, but it means you have to label your forces and calculate this and that. So in an exam, you may not have that much time to go and calculate all the forces. So you could think about this way as well, in terms of power output, how much additional power is needed to counter the force. So that is a car going uphill. Now what if you're on an escalator and you're trying to find the power of escalator? So escalator and underground station have 250 people standing and it's moving, blah blah blah. Escalator is at an angle 40 degrees. What is the minimum power required to lift all these people on the escalator? By the way, this is an escalator. Oh man, that's kind of tragic. His brains got smushed. So imagine there's a whole bunch of people standing here, 250 of them. Well, I'll just draw the people. Imagine that they're all moving up at a speed of also 4.3 meters per second. What is the power required to lift these people? Pause this video, try it out, and come back if you get stuck and see how you can solve this power question. Now, if we have power, can we use work done over time? Or should we use force times velocity? How do we decide? Well, if we use work done over time, we have to find the change in height of all the people on average. But to find the change in height, I don't think we quite have enough information, because we'll need to know like the length or the displacement of all the people on average to find the height, because we want to do MGH. So we don't have this info. So that we cannot use this. We'll need more hassle to use that. Okay, so let's look at force times velocity. How do we find the force that this escalator has to counter? Well, let's think of it this way. If I simplify this a bit, and I say this is an inclined plane of 40 degrees, and the total mass or total weight of all these people is gonna be what? What's that thing called? mg. Okay, and imagine that all these people are being lifted up at the same velocity. So wait a second, what's the total mass? There's 250 people, roughly 78 kg each. So 250 times 78 kg will give us about a lot of kilograms. So the 19,500 kilograms is the amount of weight, amount of mass that this escalator has to lift up. Okay, so let's look at energies. So this is a lot of energy to put in because of this weight, this escalator has to lift up the equal amount of weight. So let's find what's this horizontal component here. So horizontal component, like before, is going to be, this is the angle, 40 degrees, mg sine of 40. This is the amount of weight that is acting on the people on average, but that's also the amount that you need to counter upwards to get everyone up at a constant speed. So that's why we want to find what this value is. So anyway, let me just write it over here. That's kind of crowded over there. So the force needed to be exerted by this escalator is equal to the horizontal component of weight. So that would be mg sine 40 times the constant speed where all this whole chunk of mass is moving up at. So that is 40 degrees. It's 40 degrees. What on earth am I thinking? 4.3. I said 4.3. 40 degrees. So here what we have, mg, we got 19,500 times 9.81 times sine of 40 times 4.3. Whoa, that is a lot of energy. And a lot of watts. So here on my calculator, I got about 528.7 times 10 to the 3 watts. Well, but what is the answers that they give us? Let me check a bit on page 14. So they give us units in kilowatts. Alright, so let me change this to kilowatts. So this will be 5.2, if I ignore the point, 529 kilowatts. Okay. And the answer closest, they rounded to 2 SF, so that's 530 kilowatts. Notice how you may think of forces and Stuva equation, like, oh no, how to do the Stuva? You don't need to do that anymore, because now, if you want to find power, you just need to think of the force that this escalator needs to exert times the speed that all this stuff is moving up. Okay, so this is a shortcut on how you can think of moving objects. So these few questions should be good enough to help you get started thinking about changes in energy and work done on systems or by systems. And we're pretty much on this part here, this whole section. Now I need to remind you again that this section is very applied. So if you memorize, like say these 4 questions I just showed you, and you don't really understand what is going on behind there, how to apply, how to solve problems, you might find it difficult to solve other problems as well. So my suggestion for you is, for this unit is, you need to problem solve, like really problem solve, and apply the basic principles. So power is a change in energy over time, or force times velocity. So you need to make sure you don't give up. Just like, oh, I don't know how to do it. Let me find the answer. Okay, I'm satisfied. I got the answer. No. You want to stop and try to think of how can you make sense of this question so that you know how to apply the principles to other scenarios. Because you will see like all kinds of engines, machines, circuits, and systems all come out in the question. There is no like fixed formula that will always be the case for each question. So go try out the practice questions below. This one is a must try, because these few I show you are not enough for all kinds. There are a few extra weird questions. I made a list of them. But make sure you post in the questions channel, ask your friends when you come across those weird questions. If I have time, I will make a video for those weird questions. If not, I will answer questions if you post them in the questions channel. So keep an eye out for weird questions. Some are just like, what on earth is going on? But in general, remember to apply the basic principles and problem solve. Don't give up. Keep at it, take a nap, come back, and continue doing it.